Hello, how are you doing?
Good, Professor.
Hi, Josh, how are you?
I'm good, and you?
Okay. Did you have a good weekend?
Yeah, it went by a little too quick, but
Yeah,
it was all
I
good.
know. The long weekends always, Yeah, I was able to see some family. Did you go anywhere, do anything fun?
I just hung out with my family here. We
Oh,
just went to the movies. Yeah.
oh, okay. What did you see?
Sanchi, the new Marvel movie.
Oh,
Yeah.
did you like it?
Yeah, I liked it. It was really good. It was funny too.
Oh, okay, cool. I haven't been to movies for ages. Yeah, it's different with COVID now, you know?
Yeah.
Yeah, well, I'm glad you had fun. That's good. I just finished another class, so coming back to my office to teach this one. Go ahead and check out the assignment we're gonna do today. Let me know if you have questions.
Okay.
Hi everyone, how are you doing? We are in week 3, so check out your assignment for today. We'll start in 1 minute. Let me. I didn't want to post everything until yesterday because I figured that everyone is enjoying the holiday, and I hope you had a good time spending time with family or doing fun things. So we are going to do sets this week. Okay, so mostly everybody's here. We are, I guess, short a few people, but I'm going to go into screen share and hopefully maybe those people will join us. If you have questions, you can unmute and ask, or if you type into the chat, I'll try to address it promptly, okay? And so a little bit forward, we're not going to do the subsequent chapter after 3 because I want to come back to encryption down the line. 5 is encryption, so we'll come back to that. 4 is a little bit, that's going to be tied with proofing. So we're going to do chapter 7 today. We're going to work on sets. The notes that you'll find is going to be here. Okay. And then let me also open that. And then you are going to also work on the assignment when we're on the session. So you can go to the next few pages to find the assignment. We are going to do a C++ lab with sets this week. Just like last week, how we did bitwise and the operators. So last week we touched on gates, operators, the logical operators. This week we're going to switch gear and we're going to move to sets. And this is going to be chapter 7. So in the notes, it's going to start talking about sets. And you would see this in programming languages like Python or C++. There is a container called sets. So you can implement sets, and sets is a little bit different than any type of container. Your element value cannot be repeated. So let's say if I have 1, 2, 3, 4, 5, 6, I cannot have the repeating number in that set. So I cannot have 1, 1, right? 3, 4, 5, 6, so and so on. So each of the number has to be unique. And the way that we would denote sets, it also pertaining to the syntax of the language, but in general, you're gonna see that it would be using the curly brace or the braces. So sets is defined as an unordered collection of objects or elements. Most of the time we would use numerical values or integers to represent the elements in that set. But you can have a set of not numerical, right? You can have a set of characters. You can have a set of strings. But in the example exercise that we're going to be doing, we are mostly going to use integers. So whenever that you would see the n notation like this, that will be your natural numbers. Or sometime you would see in the textbook, it would use set Z that would represent integers, right? And in C++, we would have to use data type, right? When we're declaring a container, we would say int. So that means that that particular container is going to use integers. Then you can have unsigned values or positive integers that will be Z plus. And then sometimes you would have rational number, or R stands for real number, or we would just have a set with a given identifier like S, and we would use the value that are initialized in that set. So in this example, we'd see S is 1, 2, 3. So there are 3 elements in that set, and those are the numbers. So we would use a curly bracket or the curly brace to include the element values in that set. And as I mentioned before, we might have something with characters, right? We might have something with string. We might have something that would represent binary, like 4 bits, that will be our nibble. So what you see here is it's just some of the notation basics that we need to go over. Okay. So in the first part here, it shows that if X is an element of S, we would write X, E, S. Okay. So that means that it is an element in S, or it is in S. So you can have, let's say X can be 1, X can be 1,000, and that can be in the set S. If X is not in the set that is identified as S, we would use E with a slash. That means it's not an element of that set. Okay. So the way that we would denote that an element is a value is in a set is to use the symbol E, and then the slash E indicates that it is not it's not an element in that set. Okay. Now, I mentioned before that set needs to contain unique values. So sometimes you would have 2 sets that would be equal. How are they equal? Well, if the elements are the same in values and it has the same number of elements. Okay. And that's what we call cardinality. So cardinality is the size of that container, which represents the number of elements in that set. So if we have ABC in the first set, that is also equal to BCA in the second set. Now, order doesn't really matter in this case, right? We're just looking at the values of the elements in the set and the number of elements in that set. Okay. So here it says if a set has a finite number of elements, we can say that it is a finite set, and the cardinality or the size of the set is the number of elements that it contains. So just like how you've seen in array in C++, right? An array would use the square brace, and the size of that array is really going to be determined by the number of elements in that array. Similarly, we would say that the cardinality or the size of the set is the number of elements in that set. Okay, so we can also use the keyword size of in C++. So how do we write cardinality values, right? So if we want to denote the size of the set, we would put the pipe around the ID of that set. So if for the set S, you would use pipe S pipe to denote the cardinality of S. So the example here, it says if S is 1, 2, 5, and 7, then the cardinality of set S is 4 because there are 4 elements. So you simply count up the number of elements in that set. Okay. So cardinality is also defined in infinite set. So in the case where you have infinite number of elements, its size is going to be infinite, right? It would go on forever. So you might have something that's finite and you might have something that's infinite. And you also can have an empty set. So like what we would have in an empty container, like an array, you can initialize the values or you can create a container. So at that point, what happens is the computer is going to it's going to allocate a section of the memory to store the values, but we don't have any values to store yet. So for example, let's say that you would create an application where people would purchase things online, right? And the shopping cart that you see is going to be in the background. And when we program it, it would be a container. We would then, when the user would pick the product, then its price is going to go get added into that container so we can tally it up and create a sum, right, for their purchase. So just like another container, a set can be empty. That means that it has no element. So the way that you denote an empty set is going to be with a 0 with a slash or a pair of curly braces with no values included. Okay, so keep in mind that there is an empty set. Okay, so I'm going to pause here, and then what I'm going to do is I'm going to go over the assignment that we have to do today. And so I will walk you through that. Okay, so here's the assignment, and you can find this on Canvas. You can download it or you can look at on the page and then type out the answer. So what I did was I put a table for you, and this is going to be the symbol that we're going to use, because having you search for those symbol, that might take a long time. So when you write out your answer, if you're typing it up, you can simply copy and paste this symbol into your answer, and that will make it easier. Okay, so let's look at some of the symbols. So we already talked about the E is it's going to be element of. The slash E is not the element of. The empty set is the 0 with the slash or the pair of curly brace. Okay. And then later on, we're going to talk about Venn diagram, where we're going to talk about intersection. And if you took Python with me, then you already know that Python has a way that we can look at sets, frozen sets, and also mutable sets, looking at how we would have an intersection, overlapping data from one set to another. And then symmetric difference, right, where we might have some elements that have different values from one set to another set for comparison. We'll touch on that later. And then we also have a subset. We might have a group of values that will be part of the larger set, but they would be grouped together. So that will be a subset that will be indicated with like a C symbol. And then the C with the underscore here, with the line under, that will be the subset or equal to. And then the U stands for the union, and the C is just the complement, which is the opposite. Okay, so those are the symbol that we're going to use. So now we are going to practice using the symbol for the notation. For one, we would say denote A is an element of B. So we have a set B, and A is an element of the set B. So we would say A, and then you can copy the symbol and paste it here. You can type E is okay, and then put B. So we would say A is an element of B. The reason why I go over this is when we start doing exercises, you need to know how to read the notation. Okay. Then for number 2, we are going to do the same thing like number 1. We're going to denote V as an element of T. So we would say V is an element of, so we put the E and then T. And A right, can hold any value. Same thing with V, right? It's just a way that we would identify that element. It could be a character, it could be a number, and so on. Any question with the first two exercises? Straightforward, right? Then in number 3, we are going to start looking at the size of our set, right? The cardinality. And this is important because later on when we're going to start looking, we're going to compare one set with another set. We would start with looking at first the number of elements in each set. So that way we can conclude whether it's equal to or there is some difference from one set to another. So when you're looking at the set, after you're looking at the elements, you would then look at its size. So for 3, we would need to denote the cardinality of set P. Then we look at the values here and the number of elements. So we have 1, 2, 3, 4, 5. There are 5 elements in that set. So we can say the cardinality of P is 5. And you would use the pipe, right? You can find this on your keyboard near the enter button. And then you would say cardinality of P is 5. Okay, so for 3, we simply count up the number of elements and we would put down the number of elements there for its cardinality, its size. Question for 3. Okay, next we are going to look at number 4. Denote the cardinality of Q, right? And so we would start looking at the number of elements in Q. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there are 9 elements in Q. So we would say that its cardinality is 9. So we would say Q cardinality is 9. So baby step at the beginning, right? So first we look at what element is in the set, then we look at the size of the set or the cardinality. Then in following that, we would then indicate an empty set. So it's just a container, nothing is initialized as values yet. So there are 2 ways that we can write for number 5. It asks you, how do you denote an empty set F? So we would say F with the pair of curly brace like this, or we can say F with the 0 slash through it. And you can find the empty set symbol there. Okay. Any question? So in the notes, it starts with talking about, okay, I have a question. Is there a reason why there is no equal sign to an empty set? Yeah, because we don't really specialize. We don't say, it's not initialized yet, Matthew. When in programming, when you start initializing something is when you use the equal sign, right? Like, so for example, if you say a variable, like variable 1, would say int variable 1 is equal to, right? Yeah. So declaration or when we define a container, when you use the equal sign to it, then that means that you initialize. And in an empty set, there's no values for us to initialize yet. So we don't need to put an equal. Good. Good question. You're welcome. Okay, other questions? All right, so let's do set comparison. We need to do this manually. So when we program, it's going to be easier for us to kind of see what's happening, right? So for number 6, it asks you to determine if set X is equal to Y. And it tells you here that when X is 11, 99, 44, 33, 77, and set Y is 99, 77, 33, 44, 11. So when you approach this type of problem, the first thing that you need to look at, right, there are two things. You need to look at the total number of elements in each set. Are they the same, right? So if we count up the cardinality, we have X cardinality is 1, 2, 3, 4, 5. There are 5 elements. Y cardinality 1, 2, 3, 4, 5, right? Step 2 is that we need to match up to see if they have the same exact value. So they both have 11, even though, right, Y has 11 later on. Remember I said order doesn't matter, right? So it could be first or it could be last. It could be in the middle. It doesn't matter. So we would have 11 in both, 99 in both, right? 44 in both, 33 in both, and 77 in both. So they have the same exact element. So therefore, our answer is set X is equal to set Y because they contain the same elements and have the same cardinality. Okay, so we need to check the element values and the number of elements when we do comparison. Any question? So as you can see here, it's going to lead you to a little bit more advanced problem in the following in number 7. So for 7, it says to determine if A is equal to B and C. When A is -2, 55, 23, 91, 67, 82, and 10. B is 67, -2, 82, 55, 10, and 91. And C is 23, 91, 10, -2, 67, 4, and 55. Explain your answer. So like what we did in number 6, right? First thing that's the easiest for us to do is count up the number of elements in each set and compare their cardinality. So A, the cardinality is 1, 2, 3, 4, 5, 6, 7. There are 7 elements in A. In B, there's 1, 2, 3, 4, 5, 6. So there's 6 elements in B. And then C cardinality is 1, 2, 3, 4, 5, 6, 7. So there are also 7 in C. So A and C has the same cardinality and B doesn't, right? So we know right away that A and B are not equal. Next, we are going to compare the values. So to really eliminate, right, we can now just probably omit B because B doesn't have the same cardinality as A, so we can conclude that it's not equal to A or C. So we now need to look at to see if A and C are equal. -2, they both have -2. 55, they both have 55. 23, they both have 23. 91, they both have 91. 67, both have 67. But when you get to 82, you can see that C does not have 82. And when you get to 10, they both have 10, but C has 4. So that, so 4 and 82, that's the symmetric difference. So that means that the A has 82, that's different to C, and C has 4, that's different to A. So we can conclude that A is not equal to B because it has more elements than B, and B is not equal to C, and A is not equal to C because here I stated that A contains more element than B, C contains different element than B and A.
How did you get the not equal sign?
I'm sorry. Oh, yeah, you can use insert and then you can use the symbol. And usually if you don't see it here, it's usually there. But if you don't see it there, you can use more symbol and you can find it. On Word, insert symbol. Symbol is right here on the right side. And it will be here. And you don't have to use the symbol. You can, if you can't find it, you can just type it out, right? That's fine. It just asks you to explain your answer. But you can use the symbol if you like to use the symbol here. Other questions?
Professor, I did have one last question.
Sure.
In the book on, I think on page 88, they give
Mhm.
an example of a set near the top, but it has two of the same elements within one set. So is it breaking the rule there, or are they trying to
Let
make a
me
point?
see if you're, 1 second. Let me find the book PDF.
Page
You
88.
said 88?
Yeah. So where it says two sets are equal, um, if and only if.
Yeah. So that means, yeah, I use the same example, ABC and BCA and BACB. You notice that in this one, let me zoom in. Okay. See how this right here, even though there are 4 elements, remember what I said, sets, each of the element has to be unique. So when you put this into the computer, when you have a double B like this, it's going to treat it as 1 because that value has to be unique. So if I have 2 B's, it's going to combine it. And so it's going to treat it as
Oh,
BAC.
okay, I see
Yeah.
it. Yeah, so even if there's like a million of them, as long as
Yeah.
it's the same answer, it'll just see it as one.
Right. So
I
I
got
can have BBAACC. It's still going to treat it as BAC.
ABC. Got it. All right.
Yeah, they have to be unique. And that's the true difference in sets container is that your initialized value can only be unique. So you cannot have a repeating value. So if you use the set container, let's say in research where you might have results that would be the same repeatedly, it will not be a good container to use because in that sense, you would not know how frequent that outcome would be. So you might want to consider using another container. Sets is good. Data sets, a lot of the time data analysis, they use sets to really look at, right, like one set of data. So let's say that I can evaluate, you know, let's say vaccine happening in one city to another city for COVID, or I can also look at like, death rate and birth rate and from one city to another in the same county. And so I can see how that will be overlapping. It will be good to compare something like that versus if you're looking at iteration of data that might be exactly the same, that's the container set is not a good one to use. So you would see more in Venn diagram when we get to the later exercise, but yeah, good question. Okay, other questions? All right. So now what we are going to do is we are going to continue to compare. Okay. So here, just coming back to some of the content, I took some of this from the textbook and I added some things, but here you can see that they show you set might also have no element. We talked about empty sets. And when you also write it out, what happens is we looked at how a set notation can be included into an equation. So it might be like this, right? And that equation might play an important role, like part of your algorithm. That might be something that you need for calculation. So you would have set S is that X is an element of real number, that's R, and x squared plus 4x plus c is equal to 0, right? And then, we would go ahead and start putting in some of the values. When c is equal to 0, s is -4 and 0, and so on. And that's how you would solve the polynomial. But so in the set builder notation, what we want is we would have a finite set. We touch on that, how to write that out. We would have an infinite set when we would use ... to indicate that it continues. But we need to really use the set notation to describe which elements are in the set. That's important, right? We have to start with saying this element is in this set. And then we also need to say the condition of that element, how it's applied to that set. Okay, so the set builder notation, there are two parts to it. First, you would start with the element as part of the set and the condition of that element. Okay, just like what we saw earlier with the X is in the set S and then the equation for X. Then it also talks about how we can represent this in set notation. So there are some examples here, right? What you want is you want to treat the element, it could be a variable, it could be, so it might be a subcontainer, or it might be a value, and that will be part of the set. And you need to say that it is using a pipe, right? They say vertical bar, but that's a pipe, such that we would say the condition of that particular element. So we'll do some practice with this element, condition of element, and that's all you need for the set notation. Okay. All right. So let's finish the comparison first, and then we are going to do some set notation. Actually, no, right now we are going to do set builder. Sorry, I was looking ahead. Okay, number 8. It says provide the set builder notation for the following. The set of R in T such that R is greater than 7, which is equal to 3, 7, 10, 14, and 17. Okay, so first we would say that R is an element of T. That's what we want. We want to address the actual criteria that they put here. R is an element in T. So we put RET, pipe. Okay. Hold on 1 second. Let me double check something. Okay. I put a comma there, but there should not be a comma here. Okay. Then we want to say R is greater than 7. Now, if you're looking at the values that were given to us to meet this condition, right? The only elements that would be greater than 7 is 10 and subsequent values. So we can say 10, 14, 17, ... right? So we would say that R is in an element of T in which R is greater than 7, and R could be 10, 14, and 17, and so on. And that's how it's supposed to read. Any question with 8A? All right, so for the next one, similarly, we would start with the criteria that they tell us here. The set of integers such that y to the third is greater than 7, which could be equal to these values, okay? So we would say that y, and here they already tell you the bigger set is the integers, right? And if you look at the beginning of the notes, it tells you that z represent integers. So you would say y is an element of integers, which is z, and y to the third is greater than 7. This is the criteria, the condition. Okay. In which y could be 4, 5, 6, 7, 8, 9, 10, and so on, all the way to 16. Okay, because if you take 4 and you cube it, right, you raise it to the third power, it is greater than 7, right? And if you take 5, you cube it, it's greater than 7, and so on. So all of these numbers could be used for y, and y is to the third is greater than 7, and y is an element of z, or integers. So translating this to C++, right? When you see something like this, you would piece it out. You would say, okay, how do I go about creating this container? I would say that, oh, it is an integer, so data type int. So you simply say int y, right? And then you would then having to put in the condition. And in condition, we simply do what? We can do an if statement, right? If y to the third, right, is greater than 7, then we would execute, we would plug y in. Y is 4, 5, 6, 7. So what I would do is I would create another container, and then I would use a loop, right, like a for loop to iterate through each of the element and then cube it and check to see if it's greater than 7. Easy. Solve in like 3 lines. Okay. So when you hit university coding camp, which is what a lot of them are doing now, you are going to get discrete structure problem to solve. And so they would say, oh, look at this equation and write a program that represent the equation, or solve the equation using programming. So you would have to take what you've seen mathematically and then interpret that and be able to program it. And this is what this class is about, right? Looking at what we see in math theory and then apply it so you can see it as a program. Okay. Question. So from here on out, whenever you started looking at a math problem, you should start thinking about how do I solve this programming wise, right? And that's what software does for us. Everything that we do, all the functions, all the things from purchasing to, you know, turning on your air conditioning to driving your car, all of that is programmable. All right. So we see how set notation is. Let's do the next one. For C, the set of natural numbers such that y squared is less than 100 and y could be 3, 4, 5, 6, 7, 8, 9. So we can say y is an element of n and represents natural number. And y squared is less than 100. So we would put y is an element of the set and the condition for y. And y could be initialized at 3, 4, 5, 6, 7, 8, 9. And that is true because if you square 9, that's 81, and 81 is less than 100, right? Any of those values squared is going to be less than 100. Question for C. Sorry, scroll down too far there. All right, let's talk about D. This one is a little tricky, right? D says that the set of S such that S is equal to 9y, where y is a natural number, and it could be 1, 3, 5, 7, and 9, etc. But it also is a positive odd integer. Okay. So there are many layers in this particular question, right? We know that S is the set and the condition for S is 9y. So there are two ways to approach this. So first, you're going to start with looking at S. Okay. So here I said that the condition for S is 9y. And y is an element of the natural number. Okay. So if we say that, can y be part of set S? Sure. But it didn't clearly say that, right? We know that y is an element of S in that it's part of the condition, because earlier you saw that this is how we would apply, right, the values into that particular element. So the way that I would write this is a little bit different than the last one. I would say that the condition for S is 9y, and y is an element of n. Or we can write it as y is an element of n, and S is 9y. Okay. But this should, I feel like there should be another statement, a substatement that should be included in this question, where it would say that S is also part of the natural number. But we would leave it like that, like how the question is asked. And you can say that y, it could be, right, 1, 3, 5, 7, 9, and so on. So the complete answer would be something like this. Okay. Or you can also indicate it like this, and then you can say y is 1, 3, 1, 5, 7, 9, etc. Any question? Okay, so if you're looking at the notes, right, the notes also go over set notation. Make sure we know how to read set notation because you will see it on your next quiz and also on your final exam. Okay. Okay. So after that section on page 2, it's going to go over Venn diagram. And Venn diagrams is always so fun. It gives you the overall visual of how data sets or sets would be. And we would be able to use Venn diagram to illustrate, right? Like what objects that would contain or what container would be overlapping or jointed or disjointed and so on. Okay. So we would always start out with a rectangle, and that would represent the universe, everything. Okay. And to represent a group of people or a set, for example, like here, the example talks about the university student, as I'm using Northeastern University book, right? The example is to their student. Well, let's say that if we need to represent RCCD students, right? That will be this set in the universe. Okay. Or you also can have another set. Let's say that set B would represent the faculty or the teachers at that school at RCCD. That will be set B. So that will be another object or another container in the universe. And at this point, when you're looking at this picture, they are separated, right? So group A is different than group B. They are disjointed. There's no overlapping. There's nothing in common there. But when we're looking at faculty and students, yeah, the school is the commonality for those things. But if you're looking at like different populations, right? Like, you know, people in California compared to people somewhere in the world, like in Brazil. Okay. And then we have to think about like, you know, geographic, what are the characteristics? Could there be some commonality and so on? So that will be just two separate objects that there's no common overlapping relationship. There's no relationship with one object to another object. That will be disjointed. Okay. So here we say that if A is a subset of B, that means that A is included in B. We just went over set notation. So when you say A is part of B, that means that A is a subset of B. B includes A. That means that every element of A is also element of B. Okay. So it's like this. They say that if you are a student at Moreno Valley College, you are a student of RCCD, and you are a college student. So Moreno Valley College is a subset of RCCD, and RCCD is a subset of the overall college students in our nation, let's say, right? So we would then denote it as the first group, which is Moreno Valley students. A is a subset of B, and since A is a subset of B, A could be equal to B when you're using the equal notation like this with the subset. And the element of A could be exactly the same element of B. Okay. So you might have a subset that would have exactly the same value as the parent set, right? that means that it would be equal. Or in the case that one object is a subset of another object, A is a subset of B, and it will not be equal to B. So it might have less elements than B, right? A might contain 1, 2, and B might contain 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So in that case, we would denote it with just the C. Okay. So this means that every element of A is an element of B, but there might be at least one element of B that is not an element of A. Sure, right? Like we said, if A contains 1, 2, and B contain 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, B has many different elements than compared to A. Okay, so at that point, we would say that A is a proper subset of B. Okay, so the diagram that we would see that is this one below. You would have A is a subset of B, which is part of the universe. Okay, so let's practice drawing diagram. So we want to draw a Venn diagram that contains two disjointed set P and Q with the elements from the universe. Okay. So I did a few here, but I'll show you how you can use in Microsoft Word. You can use many tools online. Draw.io is a good one. If you want to cloud, it stores your drawing on the cloud. You can use, Draw, you can use Adobe product, but since we're in Microsoft Word, you're going to do Insert, Shape. You select the shape, then you drag it. And then it gives you the design tab. You can change it, the color, fill, whatever you like, right? Your liking. Then, so here's my universe. If you want to add text, you right click it, okay? And then you choose add text. So I'm just gonna, let's see, tap this back. Move, I'm gonna backspace that, so I just put you over here, right? And then I can insert another shape. And then I draw a circle. And let's make this black or something. And then right click. We can do add text. And then we can say P. And since it's disjointed, we would then need to put in another object that would represent Q, like these ones I drew, right? So again, insert, shape, draw a little circle, and then make a different color, for example, and then we can just add text, right click, and Q, like that. So at this point, we would have disjointed as there's no overlapping. There's no relationship between P or Q. But if you want them jointed, then you would have some overlapping like this, right? So disjointed, they're separated. While I'm only asking you to draw one, you need to make sure that you know how to read Venn diagram or interpret Venn diagram for our quiz and test. Okay. Any question? All right. Pretty easy there. Okay. So here it shows you how to represent subset, how to represent disjointed, and then we are going to look at the operation for Venn, which is set operations actually. So some programming language would actually have the built-in methods. That means that in its library, it already have a function that you can use to compare sets, like Python for one. I know that I covered this in my CIS-30A, where we would write programs with sets and frozen sets. Okay. So at this point, what we're going to do is we are going to use set operations to look at the relationship of two separate sets or multiple sets. Okay. So we would use a set operation such as union, and union is using a U as a symbol. So when you have A union B, right, that means A union B. And so the way that they use this example is that it says X is an element of A or X is an element of B. That means X could be here. Okay. So let A equal 1, 2, 3, 4. B is 2, 3, 4, 6, 7, 9. And C is 1, 2, 9. So when we union A, we combine everything with both sets. So we're going to take the elements from A and elements from B, and we put it all in one set container. So think of union like a marriage, right? Like when people get married, properties are shared, right? Household, two people from two homes gonna come together to one home. Your things become my things and my things become your things. So we combine everything into one container. So set A elements combined with set B elements, put it into one container, one set. When we combine B and C, same thing. We would take 2, 3, 4, 6, 7, 9, combine with 1, 2, 9. Now, notice that when you have a 2 in B and a 2 in C, it's only going to go in as 1, 2. We talked about non-repeating values. We're only going to keep one, right? So it's when it puts it into one container, when it operates the union, it's going to put one unique value instead of two twos, okay? So we have 1, 2, 3, 4, 6, 7, 9. And then the same thing for A and C. We have 1, 2, 3, 4, and C is 1, 2, 9. Then we would have 1, 2, 3, 4 from A. And then it's going to take the 9 from C and put it there because the 1 and the 2 already exists. Okay. So here we can say that for any set S, S union empty set is S, right? Like when you union a set with no element, there's nothing added, so it's still the same. When you union the universe, it becomes part of the universe. Okay. All right. Let's look at another example. We'll do the assignment. Actually, let me check your assignment real quick. Okay, so let's answer this first. Okay, so number 10, it says determine if the following statement about Venn diagram is true or false. A, if R is a subset of S, R is included in S, or S includes R, then every element of R is also an element of S. We saw this in the example, so true. So if you have, let's say R contains 1, right? And R is part of S, so that means that S also contains 1. And R is included in S, or S is included in R. So every element of R is an element of S. That means that they're equal, right? If I'm a subset of something and that something is a subset of me, then that means that I would have the same content as that subset, right? So true for A. For B, every element of G is an element of H. but there is at least one element of H that is not an element of G. So there's a difference. We conclude G is not a proper subset of H. False. So I tested with this with the value. Let's say that G is 1, 2, 3, 4, and H is 1, 2, 3, 4, 5. It has one more, right? Because it says H has at least one element that is not in G. So 5 is not in G. So G is the proper subset of H. Okay, this word not is incorrect. Because if you look, right, it is a subset. It's right here. Okay, so false for that one. Then for 10C, it says if X is a subset of Y, but X is not equal to Y, yeah, that could be true. So we would say true because X could be 1, 2, 3, 4, 5, and Y could be 1, 2, 3, 4, 5, 6. Just like the last one, it is a proper subset, right? Up to here, and it's not equal. Sure. So that's true. Any question? Okay, so we can do 11 because we just pretty much do union for 11. It's pretty easy. 11 says X is 10, 20, 30, 40, 50, Y is 30, 40, 50, 60, 70, and Z is 10, 50, 100, 200. Complete the following operations. First, we're going to union X and Y. So we're going to combine X values with Y values into one set. So I would take 20, 10, 20, 30, 40, 50, put that here. And since 30, 40, 50 already exists from X, when we combine, we only need to bring down 60 and 70 there because we have to have unique value. They cannot be repeating. Then we do the same thing for 11B. We would combine the elements from X and the elements from Z. So X, I have 10, 20, 30, 40, 50. Z, I have 10, 50, 100, 200. Since 10 and 50 is repeating, I don't need to bring that down. I already have it. It already exists from the X. Then I just need to add the 100, 200. So this is what happens in the back, right? The computer, let's say that you write the C++ program for this. When you initialize, you declare, let's say that this is the set and this is the set. And when it needs to combine and output as a set, right? What it's going to do is that it's going to look at, it's going to push in these values, okay? And it's going to check when you're using the set header file, it's going to check to see which values are already in the set. If it's there already, it's not going to add it. If it's not there, when you do a union, it's going to add the new values, okay? The difference from the second set. And then for C, we are going to do the same thing like the other one, but with Z and Y. So Y had 30, 40, 50, 60, 70, right? And then Z has 10, 50, 100, 200. So it's going to push in these values, 30, 40, 50, 60, 70, right here. And then we are going to add 10, but not 50 because 50 already exists from the Y. And then it's going to add the 100 and the 200 to the new container. Question? So you should be expecting to understand how to do this for quiz and exam. You will have questions similar to this on the test and quiz. Okay. Next, we're going to talk about intersection. Do you have any question for union? So union, you combine everything. If it already, that value already exists in one set, it won't add it the second time, right? It's going to add in the different value from the other sets. So we would have one container with everything combined. For the intersection, here's the intersection. So union, we saw that it's going to look at both everything from A and B. For the intersection, it's only going to look at the common things between A and B. Okay. So the example here is A is 1, 2, 3, 4, B is 2, 3, 4, 6, 7, 9, and C is 1, 2, 9. So when we have an intersection of A with B, we would look at the common values between A and B. So we know that 2, 3, 4 appears in A and also in B, 2, 3, 4. So that will be the intersection values. Okay. And then again with B and C. So the intersection of B and C would be 2 and 9 because 2 and 9 appears in both of the sets. So that will be the common values that you would see in both sets. And the same thing with A and C. We see that A has 1 and 2 and C has 1 and 2. Right? It's going to drop off 9, 3, and 4 because that's not common in both sets. And it tells you here that for any set S, S union empty is empty. Okay. And S union the universe is S. When set A and B are disjointed, if and only if A and intersection with B is an empty set. Because when you separate them, right, there's nothing in common. They're disjointed, so that will be an empty set. No elements that's initialized for common, both sets. So the intersection with A and B is an empty set. If A and B are finite sets, the cardinality of A union B is given by A union B is A cardinality of A plus cardinality of B subtracted by the number of elements that's in the intersection. Okay, that's how you're going to find the cardinality of union. So that will bring us to what is known as principle of inclusion and exclusion. When you're looking at the sets, right? We add up the cardinality of the first set and the second set combined. We include those, okay? Then we also have to exclude the intersection, the overlapping values, the common values between these two sets, because we don't want to count them twice. So that's why we have to subtract the intersection of those sets. Okay. Otherwise, you would double count them and that won't be right. Because if I have 5 in A and 6 in B combined, I would have 11, right? But look, I have something that's overlapping. So I have to exclude those. So that will be part of our principle of inclusion and exclusion. You will see this again when we do probability and accountability and countability in the next few chapters. This will come up all the way through the end. Okay, even when we talk about pigeonhole and all of that. Okay. All right, so let's do the next question. For 12, we're going to do intersection. R is 5, 10, 15, 20, 60. S is 10, 15, 25, 35. And T is 15, 25, 35, 45, and 60. We want to determine the intersection for A. R intersects with S. So you simply look at the values that they share. That's the same in both sets. We know that 10 is the same, right? 15 is the same. And that's it. So we have 10 and 15. So there are two elements that would be the intersection of R and S, R2S. R intersect S at 10 and 15. Then we go again with B. So S intersects with T. So you look at set S, which is 10, 15, 25, 35, and T is 15, 25, 35, 45, and 60. We see that 15 show up in both, 25 also show up in both, and 35 shows up in both. So that means that 15, 25, and 35 is the intersection of S to T. Okay, then we repeat the process for C. R intersects with T. So R, we're going to look for values that will be the same with T. So we know that 15 shows up in both, right? 60 shows up in both. The other ones don't. So 15 and 60. Okay, so now you have a little bit of practice with intersection for number 12. Any question? This one's a little longer than usual, right? Because usually my assignment's a little shorter, but we do have a lot of time still, right? And we have to cover some of the stuff that would come up also in the other chapter. So, all right, let's talk about complements. We touched on 2's complement the first week, but simply the complement is here is the opposite. Okay. So we would use the C to indicate the complement, or sometimes you would see that they would put a bar on top of the set identifier that would also indicate the complement. So the example here you have is A is 1, 2, 3, 4, and B is 2, 3, 4, 6, 7, 9, and C is 1, 2, 1, 2, 9. Universe is 0 through 9. So the complement of A is 0, 5, 6, 7, 8, 9. Why is that? Because what's in the universe that A does not contain? Okay, so 0 exists in the universe, but not in A. 1 is in the universe, and it is in A, so we cannot include 1 in the complement, right? And 2 and 3 and 4, but 5 is in universe, but it's not in A. So we would, in the complement, we would include the value that exists in the universe, but it is not in the set. Okay. And so, and the same thing for B. B have 2, 3, 4, 6, 7, 9. It does not have 0, which is in the universe, 1, which is in the universe, right? It has 2, 3, 4. 5 exists in the universe and it doesn't have that. So put 5 and then 8. Okay. So the way that we would say this is what's outside of that set that's in the universe. That's what we're going to count as a complement. Now here it states that the empty and the universe sets are related to the complement of the empty set, which is the universe, and the complement of the universe is the empty set. Okay. And last week we touched on the logical operator, right? And we talked about how we would use the not operator to really represent the ones complement, right? In the binary level, we would say that. But when you say if, right, A is not 7, right, it could be any other number in the universe. So you can see that now tying back to how it would assess based on the condition. If B is not 120, well, it could be 130, or it could be 1, or it could be -1, right? Anything that's outside of that. Okay, so that's why you would see that there. Let's take a look at our assignment now. For 13, it says find the complement for X, Y, and Z. For X, X is 20, 30, 40, 45. And Z and Y is 25, 30, 40, 50, 55, and 60. And Z is 30, 35, 50, 55, and 65. And it gives you the value for the universe. So the complement of X is, right? I would take the value that's in the universe, but not in X. I put it there. So 10 is in U, not in X, right? 20, I cannot use 25, right? X doesn't have 25, so I put 25. 30, it has 30. Then 35 is in the universe, but not in X, so I put 35. 40, skip that one. It's in both. 45 is in both, and then the rest, right? 50, 55, 60, 65, 70, 75, and 80. And this is the complement for X. And then again, we would do the complement for Y. Y has 25. Universe have 25, so we can put 10 and 20. It doesn't have 10 and 20. There. 25 it has, 30 it has, 40 it doesn't have 35, so we can put 35. And then 50, it has 50, 55, it has that, 60. So we can put 45, right, 65, 70, 75, and 80. So basically the complement, what it is you're looking at the difference between that set and the universe, right? Or actually the difference of the universe to that set. Because if you do the other way, it's slightly different. But yeah, the difference of the universe to that set. Okay, I didn't do Z, so please do Z. That's easy. So you can put, Z and then add your C, a complement, and then put down the complement for Z. Any question?
Is it always going to be the difference within the universe, or what if there's multiple sets? Is it like a rule to follow?
Yeah, so we would look at symmetric difference and the difference because there are, okay, so when you say difference of, when you do the comparison, you would say difference of set A to set B, we are comparing A to B, right? So remember what I said earlier, I said the difference of the universe to set X, you are comparing the universe to the set. So because if you do the difference between X to the universe, it's only going to look at the X elements against the universe. So it's going to omit everything that's not included in X. So yeah, later on you're going to see, we're going to look at like the both side of the difference or one side of the difference. And that is important because the way that they write the functions for the program, it's how you compare from one set to another set, not the other way around. Okay, because if you do X to Y and Y to X, the outcome is different. Okay.
That makes
So,
sense. Thank you.
Okay. All right, so please complete Z for number 13. That's the only one I didn't do. Occasionally I don't do some of it, so you can do your own practice, right? Because I can't just give all the answers. It would not be fair. Okay. Okay, so after you look at the complement, we're going to move into difference. And this is on page 5 of the notes. So the difference is when we're looking at set A to set B, right? We would indicate A minus B. So if A is 1, 2, 3, 4, and B is 2, 3, 4, 6, 7, 9, right? We would see that A has 1 that is different than B. It does not care about 7 or 9 back here, right? Because we're comparing A to B, right? We're taking A subtract B. So the only difference in the element is the 1, right? Because 1 doesn't appear in set B, okay? But if we look at the difference from B to A, is that now we're going to take B, we're going to subtract A. Well, B has more elements than A, right? It has 6, 7, and 9 that is different than A. So we would include 6, 7, and 9. Okay. Just like I mentioned, when you're looking at from one set to another set, the difference, it's not the same as doing the second set to the first set. So if we do the difference from first to second, it might not be the same as second to first. And this is the proven case, right? And then we're going to compare B to C. B has 3, 4, 6, 7, right? C doesn't have that. And we're going to disregard the 9 because we're comparing B to C. And then again, C to B and C to A. So the way that we look at the difference is that which set are we comparing it to, right? And we are going to have that the original set, the first set is what we're going to look at the difference for. Okay, so here let's do our exercise so you can practice. We are going to look at the difference for set A to B for the first one. So A has 2, 4, 6, 8, and 10. B has 4, 5, 6, 7, 8. Well, A has 2 and B does not, so we put a 2. A has 4 and B does, so we skip that one because they both, it's in the same, right? It's the same in both sets. 6 also, right? Why didn't we put 5? Well, we're looking at the difference from A to B, not the other way, okay? So 6 is in both, so we skip 6. 8 is in both, we skip 8. And then 10. 10 is the difference of A to B. So 2 and 10 are the two values that are different from A to set B. And then again, we are going to do B to C. So B has 4, 5, 6, 7, and 8. And C has 1, 3, 5, 6, 7, 8, 9, and 11. So B has 4 and C does not, right? There's no 4 here. 5, 6, 7, 8, it has that. So that's it. Only has one element that's different between B to C. 4. And then lastly, we are going to do the difference from A to set C. So we know A has 2 and C doesn't. So that's a 2. Next number is a 4. There's no 4 in C. We put a 4. Next number is 6. 6 is there, so we skip that. 8. 8 is there. We skip that. And then 10. 10, it doesn't exist in C, so we put 10. So 2, 4, 10 are the values that are different between set A to set C. Any question? Now, when you do this in C++, right, you would say include sets, and then you would use some of the methods that are already incorporated in that library, right? And also in other languages too, like Python. Like in Python, you can do is difference and an asymmetric difference for the sets. Question. Okay, so be expected to know how to identify or find a result for difference, right, for multiple sets for quiz and exam, along with union, intersection, and complement. Okay, we're almost there, just a few more. Okay, so we are going to do number 15, which is a symmetric difference. And so if you need to reference the notes of the text, there's a section on symmetric difference. It's indicated with the delta symbol. So A delta B. So the example here, A is 1, 2, 3, 4, and B is 2, 3, 4, 6, 7, 9. If we're looking at the symmetric difference, right, we are looking at the values that exist in that is different in one set to another set and vice versa. Okay, so we're going to look at both differences in both sets. So A has 1, B does not, so we list 1. 2, we share and they're the same in both, so we skip that. 3, the same in both, we skip that. 4, same in both, we skip that. But B also have 6, 7, and 9, so we list 6, 7, and 9. Okay. Earlier, when you did difference, you just disregard what's different in the second set. In symmetric difference, you have to list all the differences in both sets. Okay. And then again, for B delta A, we list 1, right? We list 6, we list 7 and 9. 6, 7, and 9 is different in B, and 1 is different in A. As you can see, A delta B is the same as B delta A. Okay, symmetric difference is the same. All right, let's do the next one. So for 15, we have D is 1, 3, 5, 6, 7, 9, and 11. And then E is 2, 4, 6, 7, 9, 7, 10, I'm sorry. And then F is 3, 4, 7, 12. We want to determine the symmetric difference between D and set E. So D, we'll start with 1. 1 is different than E, right? There's no 1 in E, we list 1. And then 2 is in E and not in D, we list 2. 3 is in D, not in E, we list 3. 4 is in E and not in D, we list 4. 5 is in D and not in the other one, we list 5, right? 6 and 7, they share the same, so skip those. Then 9 is in D and not in E, we list 9. 10 is in E and not in D, we list 10. And 11 is in D and not in E, we list 11. Okay, so we look at the differences in both sets. And then we repeat the process for step 15B. So we would do E delta F. We're going to compare the difference in both sets. So E has 2, the other one doesn't, so list 2. F has 3 and E does not, so put 3. 4 is in both, so you skip 4. Okay, 6 is in E and not in F, you put 6. 7 is in both, so we skip 7. 10 is in E and not in F, we put 10. And then 12 is in F and not in E, we put 12. Okay. And then you can do C. Set D delta F. So the difference, the symmetric difference between D and F. Pretty easy. Take a few seconds to do that, right? So look at the difference in both sets and list them. Question. So the next part we're going to go over is the power sets and Cartesian products, right? Like this stuff, like set cardinality, Cartesian products, it's going to get carried into some of the other chapters later. So want to be able to cover. Okay. So how can you determine power sets? And let's start with the example here. If A is a set, the power set of A would include all the subsets of A, right? All the subsets of A. So can I have a subset with one number? Sure, you saw that, right? We can have a subset of one number. We can have a subset of two numbers. We can have a subset of three numbers and so on. So if A has 8 numbers, we can have many subsets. Okay. So let's look at the example. If A is 1, it contains 1 and 2. The power sets of A would be the first that will be empty set, right? The container itself. And then it might have a set that just contains 1 or another set that contains 2. Then it might also have another set that would contain 1 and 2, right? Because we said that a set can have a subset that's equal to it. It can also have an empty set, or it can have a subset that has less element. So the elements of the power sets of A are sets, right? They don't have to be numbers. They could be values. They could be anything. So in general, the cardinality of the power sets is going to be, we would use 2 to the A power. Okay. All right, let's look at the next example. So we have a set that has A, B, C, D. So the first subset is going to be empty set. And then we would have the next step is going to be a subset of one element, right? It would be a subset that has A only, B only, C only, and D only. Then we would have a subset that has 2 elements, AB, AC, AD, BC, BD, and CD. Then again, 3 elements, ABC, ABD, ACD, BCD. Then a subset of 4 elements, okay? So if we combine all of them together, right, you have the empty set first, the single element subset, the double element subset, the triple element subset, and the quadruple element subset. If you count them all, you would have 16 subsets. So the cardinality of the set S is 4, right? You would use that value as the power with the base 2. So it would be 2 to the power of n, where n is the cardinality value, okay, of the set. Okay. All right, any question with this? The tedious part of this is just you got to write it out. Okay. Okay, so you saw that I put something down for 16 there. So we want to find a power set of S given that S is 2, 3, 4. The first step is you are going to list out all the subsets. Okay. And you can sum them up, or you can find it using the equation 2 to the power of n, where n is the cardinality. So the subset of 0 element is the empty set. The subset of 1 element, I have 2, 3, and 4, and you put them in curly braces like that, and you separate them with a comma. Okay. Then next, I would list the 2 element subsets, 2, 3, 2, 4, and 3, 4. Okay, 2 elements. And then lastly, I would then list the subset of 3 elements, 2, 3, 4. So if you count them all, I have 1 set, 2, 3, 4, 5, 6, 7, 8 subsets, right? So if you total them up, there are 8 subsets. But what if you have a set that would be very large cardinality? Well, you simply take 2 and raise it to the power, which is the cardinality that gives you the power sets, which is in this case 8, because there are 3 elements. Okay, so make sure we know how to find power sets, or right, what it is and how we would approach it. Question? So the cardinality for my power sets is 8. There are 8 subsets. So when you see your power sets, it's just the number of subsets. Any questions? I only have Cartesian product left and I will be done. I don't know why Zoom showed me that. I guess there are times that it cuts out my screen. I guess the traffic might be. Okay. All right, any question before we move into Cartesian? And this stuff is important transitioning to combinatorics. We're going to do combinations and permutations. All right. Similar to some of your statistic class or math related courses. Okay, last part is Cartesian products. So basically it's an operation that returns a set from multiple sets. Okay, so you might have 2 sets that you need to find the product of those 2 sets. Okay, and here, and Cartesian product is named after Rene Descartes, and using sets as in what we would look at pairs to really evaluate and compare. So let's look at this example. Let's say that if we have A is 1, 2, 3, and B is A and B, lowercase. If we multiply them, right, if we need to find the product of the 2 sets, we would have the first value here, the first element, pair with the first element in the second set. So we have 1 and A. And then the first element pair with the second element of the second set, 1 and B. And then 2 with A, and 2 with B, 3 with A, and 3 with B. So then we would be able to visualize it. Okay, how that would be. So in general, we would have the cardinality of one set multiplied by another set to give us the product for the cardinality. So in the case where we would do triple, where we would take one set multiplied by another set multiplied by another set, that would be best graphed and represented in 3-dimensional space. So in this example, if A is 1 and 2, 1, 2, and then B is AB and C is XY, we would have a tuple 1AX, right? That will be the first element of each set, and then we would have the combination of the subsequent elements. We would have one AY, one BX, one BY, and so on. So that will be in general, we would then take the cardinality, right, of the first, multiply it by the second, and eventually a to the n. So basically we would pair them up, or in this case, we would set them up in tuple in threes and be able to represent them as products. Now, the important things that you want to look at is the laws in math. Cartesian product, A, set A with B is not cumulative. So A times B is not equal to B times A. Okay. Cartesian product is not associative, meaning that when you apply associative rule, right, A times B times C in the parentheses is not the same as A times B in the parentheses times C. And this has been proven with using different math laws. So keep in mind that these are some of the criteria for that. Okay. All right, so on the next question, we are looking at Cartesian products for 17. Given T is 2, 4, and U is 6, A, and W is 1, 3. Determine the Cartesian product for T times W times, T times U times W. So I highlighted this so that way you can see. So we're gonna take the first element, 2, 6, and 1. We're gonna make it a tuple, right? Which is a group of 3. Then we're gonna take the first element of the first and the second set, and then the second element of the third set. So 2, 2, 6, 3, and then we switch them up. Okay, so 2, 6, 1, 2, 6, 3, 2, 8, 1, 2, 8, 3, 4, 6, 1, 4, 6, 3, 4, 8, 1, and 4, 8, 3. So if we take the cardinality of T, which is 2, multiply it by the cardinality of U, which is another 2, multiply it by the cardinality of W, which is another 2, we would have 8. So that will be, if you count them up, there are 8 tuples for the outcome of Cartesian product. Any question with 17? So if you don't know how to do the cardinality multiplication, right, they basically count up the element, multiply it out. And if you want to know the details in what the product would be, right, we have to write it out like this. So basically they are combinations of the element values in those sets combined. Okay, so those will be tuples as we have 3 sets. So in Python, tuple is also a container. It's like, it's similar to an array, but you can't modify it. So when you put it in a tuple, it stays the same. You can store it in there, but unless you put it into a list, then you can modify it. So you see tuple being used in some programming languages like that. Okay, lastly, number 18. Any question with 17 before I transition? And when we finish 18, you'll be done. Okay, So it talks about how the computer represents a set, just like number sets can be represented with 0 and 1s. So first, the order of the elements in the universe, it would use bits, right? Like 0 and 1s. And so the length is the cardinality of the universe used to represent the subset U. Each position of the bit string corresponds with the element U. And a 1 in some position means the corresponding element in the set of the 0 means the element is not in the set. It sounds very confusing, so here it is. So all of that stuff that I taught you with the binary conversion, that already happened, okay? So you can't go back to that. So when I say, okay, so here's the universe, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And then so what it would do is we already initialize this value in the memory. It's a container, okay? So the binary value already exists. So what happens is that it would represent each of these value as ones. Okay, so 0 is there, 1 is there, 2 is there, 3 is there, 4 is there. So the bit position just represent that that number actually is there. It's initialized, it exists. Okay. So in this case, it would know that all of these value exist by all the ones turning on. Okay. So when you define a set, right, you would say, okay, my set is 1, 2, 5, 6, 7, 9. Each of the element, yes, there is already a binary value, right? Like this will have a binary equivalent to 1. This already have a binary equivalent to 2, and so on. But what it's going to do is going to use bits also to represent what values are there and what's not. Okay. So how does it do that? Okay. All the elements are in U. So if I have 1, look at 1. 1 is in the universe. It's gonna check against U. Remember how we talked about the complement earlier, right? It's gonna turn on that 1 because 1 exists. 0 doesn't exist in set S, so it turns it off. 1, number 2 exists in set S, it's gonna turn that 1 on. Right? 3 and 4, right? S doesn't have 3 and 4, it's gonna leave 0. Right? 5, 6, 7, 8. I'm sorry, 5, 6, 7. Those 3 are here. So it's gonna do 1, 1, 1. And then 8, it's gonna turn that off because it doesn't exist. So basically the representation of this is the complement that we talked about earlier. It checks the universe against that set, and it used the byte to represent whether the value actually exists within the universe. Okay? Question. All right. Let's do it. This is not hard at all. Like students, they always get confused about this, but it's super easy. So first, you're going to look at the universe. I have 0 through 9, just like the example, okay? And I have set A. Set A is 2, right? So the first 2 number in the universe doesn't exist, so it's going to go 0, 0, right? 0 and 1 is not there in my set, so it's going to say 0, 0. When it gets to 2, it's there, so it's going to put a 1, right? Because 2 is in the universe. Okay, so 3 is also in the universe. It's going to put a 1. 4 is not in the set, so 0. 5, it's in the set, so it's going to put a 1. There's 5 here. 7 and 8, it's in the universe and not in my set, so it's going to put 0, 0. I'm sorry, and then also 6. So 6, 7, and 8. It's not in my set, so 0, 0. And then 9 is in the universe. So it's but one. Okay. Again, I'm just going to do B with you, but you have to do C. Okay. So we're going to start with the 0, right? Set B doesn't have a 0. So 0, it's off. It has a 1. The universe has a 1. Oops, sorry. Then we would have a 1 there. 2 and 3. It does not have 2 and 3. So 0, 0, because B doesn't have 2 and 3 here. 4, it does have. So that will be 1. 5, it does not have. So 0. 6, it has. So 1. 7, no. 8, yes. 9, no. Right? And that's for B. And you can do C. And look at that. My timing is just right. Any question? Okay, so no question. Great. I will stick around for a few minutes in case you have questions until 8 o'clock. But if you are done and finished, type in your name in the chat for attendance record. I'm going to stop